This is a continuation of what we discussed in previous video about the synthesis of nanoparticles. I quoted a couple of general techniques which are available to make nanomaterials. Now in this video we will discuss a very important technique of making nanoparticles. In fact, I would say worldwide presently almost majority of people make nanomaterials by this route. It has a very appealing product, and now we will discuss this technique in detail. It is called chemical or a solution or a colloidal method of making nanoparticles. It has a couple of advantages. Number one, the technique is quite simple. Second, it is an inexpensive technique to make nanoparticles. Here, temperature is quite low as compared to the techniques which we discussed earlier. That is, highest probably around 350 degree. Otherwise, you can make nanoparticles even at room temperature. Large quantities of material can be made. This is very important because wide range of nanomaterials can be made. In fact, you can make nanomaterials which are metallic, semiconductors, insulators, etc. Still more interesting is this technique permits to have various size and shape of nanoparticles. This is in fact a very powerful parameter. The technique is so simple and low temperature. In fact, in the process of synthesis, that is during the synthesis, you can try to dope material, that is electronic doping. You can try to have the doping or dopants incorporated into the material quite easily. And it is a solution based technique, as the title says. That's the colloids. You can make solution of nanoparticles. You can later convert that to powders, even with thin films. Still more important is you can have a self-assembly. This is very interesting aspect. Once you have a nanoparticle as a colloidal solution, by creating certain conditions or very simple conditions, simple immersion, you can try to convert them to the films in a self-assembled way. Sometimes even forced assembly also can be achieved. It is, as I said, low cost. Already I said there it is inexpensive. Leave just this last one. The basic concept of this technique goes like this. It is co-precipitation concept. I have a solution wherein I have plus type of ions. We know A plus or plus type of ion which have lost electrons, we call them as cations, because under electric field they move towards negative electrode, that is cathode. We also have the ions which have gained electrons, that is a B minus. Under influence of electric field, these ions will move towards anode, therefore we call them as anion. If I take the solution which contains cation, separate solution which contains anion, mix them. The moment you mix, they will co-precipitate because of opposite charges. The resulting material is a AB. Simple example of converting sodium plus or a chlorine minus is our table salt sodium chloride. You dissolve that in water. What you generate is Na plus and Cl minus ions. So the chemical phenomenon that happens here, either it is simply a precipitation, as I said, there can be reduction route. In a reduction, you donate electron to the required ions so that they will get converted into atoms, and those atoms join together and form nanoparticles. There can be also a process of oxidation. You strip off electrons so that they undergo reaction. As a result of that, you have the material. Here, very simple reaction has been shown. As I said, you take solution of anion cations, you take zinc ions, Zn++, solution of sulfur ions, S-. When you mix them, you will have zinc sulfide as a precipitate. By controlling conditions, you can have the nanoparticles of zinc sulfide. The simplest geometry of this synthesis goes like this. You can have a flask, a hot plate, stirrer. You add solution A and solution B and control the conditions. And you can also put the condenser so that when you heat it, solution doesn't go out, it will condense and fall back so that the required molarity can be maintained throughout the reaction. You also can have a probe to measure temperature of this, and also you can have inlet so that you can access the solution from this time to time. Well, there can be many parameters of this route of colloidal synthesis, like the concentration of ions play important role. pH of bath can be controlled so that you can try to tune the parameters of nanoparticles. Temperature can be tuned, and the nature of solvent what you are using, that also decides the final product. Here two simple examples are taken to just convince how this technique works. If you take a salt of zinc chloride, say you dissolve this in water, what you generate is a zinc++. Of course, Cl minus ions will also be generated. Another solution, you try to dissolve Na2S, that is a sodium sulfide. You generate Na plus ions, sulfur minus ions. You will have in this solution S minus, in this solution zinc++. When you mix these two solutions, what you see is a co-precipitation, that is a zinc sulfide is formed, and as per this chemical reaction, sodium chloride is also formed. But this sodium chloride is soluble in water, therefore it will not be in the form of a solid, but it is in the form of ions Na plus Cl minus. Second example here is about the oxidation. Once again, zinc chloride, you dissolve this in water, you generate zinc ions, to which you add sodium hydroxide. Under this condition, zinc hydroxide is formed, ZnOH twice. Then of course, by this chemical reaction, you have 2 NaCl. So this zinc hydroxide is not completely converted to zinc oxide. You need to heat it. That we call it as a calcination process in open condition, because it has to be oxidized. Therefore, even if there is oxygen in atmosphere, that will not harm it. It will help to get it converted to oxide. So when you take zinc hydroxide and heat it, that is a calcination process, what you get is a zinc oxide, and water goes up, water vapors. And this zinc oxide will be in the nanoform. By controlling conditions of this reaction, you can have desired particle size and other parameters. Now I want to tell two important parameters of nanoparticles. Already we have discussed one of them. So important features of nanoparticles. Number one, quantum confinement effect. Already we wrote the required quantum mechanics, and finally we obtained the solution of that particle in a box. I said you earlier what is quantum confinement effect. We can simply state that in this way: size dependent optoelectronic properties can be achieved through quantum confinement effect that we have seen earlier in detail. Second aspect of nanoparticles that is quite important as the quantum confinement effect, is a large surface to volume ratio. Here I would like to just convince you with a simple example. What does it mean? Suppose you have a solid, one single piece of bread. Say the bread has this dimension: length is 10 centimeter, width is 10 centimeter, height is also 10 centimeter. So you clearly see this rectangular bread has two important parameters. One is a volume of a bread. The volume of the bread is length multiplied by breadth multiplied by height. Also, this object has certain faces. There are 6 faces. One is top, another is bottom. 2 side face, corresponding side face. 4 this face and its opposite face, totally 6 faces. And each face has certain area. And if you calculate area of each face and add all of them, that is area of 6 faces, what you get is the surface area of this bread. So we have two parameters. One is volume of bread, second is the surface of the bread. So you can make simple estimate like this. Let us see that volume 10 centimeter multiplied by 10 centimeter multiplied by 10 centimeter, that is 1000 centimeter cube. Surface area, there are 6 faces. Area of the each face, I have taken same length, width and breadth and height just for sake of simplicity. Each face has area 10 centimeter into 10 centimeter, that is 100 centimeters square. So the total area 6 multiplied by 100, that will give you 600 centimeters square is the surface area. Now we have two numbers. One is the volume of the bread, that is 1000 centimeter cube. We have total surface area of the bread 600 centimeters square. Suppose you do this. You cut bread into fine slices. Just assume that bread has been cut into 100 slices. And say during the process you have not lost any material. Just for sake of simplicity, in reality you will lose material. But don't worry about it, that is a small correction. So no loss in the thickness of the material, just you have softly cut the bread into 100 pieces. If you calculate volume, that will again approximately remain as 1000 centimeter cube. Now this is the first surface piece, that is other side. In between you have created 98 additional surfaces along the length. So as an approximation, if I want to calculate surface area, I would say 98 multiplied by original surface area. If I do that, 98 multiplied by 600 centimeters square, what I get is a 58,800 centimeters square. What is that we have done? Simply it is the same material, but I have divided material into many number of pieces, and what you see is this: there is a significant increase in the surface area. 600 centimeters square has gone to 58,800 centimeters square. It is really amazing. It is exactly taking bulk material and dividing it and converting it to nanoparticles. It means when I convert a material into nanoparticles, I am going to create large surface area. Large surface area means the atoms which are sitting on the surface are not like the atoms which are sitting in the bulk. Why it is so? It is because the atom which sits inside bulk of the material, it will have the complete bonding. Suppose you take silicon as example. Silicon has valency 4. It has a 4 neighbors, and it will have 4 neighbors completely by sharing 4 electrons. But however, if the silicon sits on the surface, only inside bonding it will have neighbors, but other side it is a air, there is no bonding. So we know that the atoms which sit on the surface with not complete bonding, we call them as surface atoms, and also it is referred as a dangling bonds. In nanomaterials, when we make any material as a nanomaterial by this colloidal route of synthesis of nanomaterials, we have to remember that once we convert a material to nanomaterial, there is a large number of surface atoms sitting. They seek chemical bonding with other materials. The result of that is, if I put such a large number of nanomaterials, they coagulate, they come together, they try to grow. Either one nanoparticle can go and attach to another nanoparticle, or they can join together and grow as a single particle. So in order to avoid that, in order to maintain the identity, that is the size of nanoparticle, we need to have capping of nanoparticles, and this capping, chemical capping, is normally done with organic molecules. So the basic concept of capping goes like this. Say you have a nanoparticle, then on the surface simply arrows are shown to just show that it has a dangling bonds, that is unsatisfied atoms on the surface. So one of them is shown here. Now you bring an organic molecule, simply a tail has been shown and there is a end atom. If we try to choose organic molecules for a given nanoparticle such that the two end atoms, the surface atom of nanoparticle and the end atom of organic molecule, can easily bind so that a good chemical bonding can be created. If that can happen, then what you can do is you can try to attach organic molecules on the surface of nanoparticle, and this process is called capping. Capping is very important to impart stability of nanoparticles. Capping is also important to make the nanoparticles more functional. In fact, it is a very interesting topic, and a lot of research is going on to make or create the desired or the required kind of nanoparticles. So there are many organic molecules which are quite reactive towards metals. Thiols are very well known. Here is a tail, then you have end as a sulfur. Similarly, you can think about alkene, again Ln at the end double bond, which is unsaturated organic compound. Easily it can react, donates this electron to have chemical bonding with surface atom. And alkynes, where there are triple bonds, highly unsaturated, more unsaturated than alkenes. Similarly, one can think about biomolecules which can combine and have the capping. And the capping is as I said, very interesting topic, because a lot of research has been done, and that makes nanoparticles more and more functional for various applications. It could be electronic devices, it could be chemical sensor, biological sensor, etc. We will stop our discussion at this point.